Okay, so in the previous videos, what happened is the 1D Leibniz case was derived. So for the 1D Leibniz case, there's simply a function of x and t that changes or deforms with time. And then the central part of it is this partial derivative that it's integrated over. And the ends basically depend on the function at the location on the boundary at t naught, and then multiplied by the rate at which the boundaries are moving. So this is the 1D Leibniz case. Again, the derivative of the function with the time-dependent boundaries, partial derivative between the two boundaries, and then the end multiplied by the time by its velocity of the end boundary and the other end boundary. So with the 2D Leibniz rule, basically instead of a function of x and t, it has a function of x, y, and t. So there's now two variables in the integrand. And instead of being integrated over two different locations on the x-axis, it's now integrated over an area. And then there was the d by t dt on the other side. So to see how this works, basically look at this graph. So this is the graph of the function of x and y. So just as a static function, it looks like this. So it's some sort of surface in space. And then the idea is to integrate over an area up to the top of the surface and then find how that volume changes with time. So without the t dependence and without the derivative, this integral would just be, this part of the integral would just be integrating inside the cylinder up to the top of the surface. So that would be some type of volume in space. However, the whole thing is time dependent, which is why the derivative with respect to t is non-zero. So there are two things that basically happen here. The first is the function in x and y at t naught, it's going to be one value, but as time progresses, so this is taken a time delta after t naught, so a very small interval over time after t naught, the function of x and y is going to deform. So it might do something like this, where it kind of rises a bit, and maybe becomes a bit more curved or whatever. So that's going to cause changes in that volume integral. And the other factor that will cause changes is the fact that the area itself is going to move or deform, because the area is also time dependent. So it basically starts here and then slides over there after an interval of delta t. So looking at this all together, so the first part of this integral is fairly simple. So this is the d by dt, and just supposing the area wasn't moving at all, so this is the equivalent of the fixed boundary case, it turns out that this is the same as it was with the boundary fixed. It's just the interval go over the area, and the d by dt basically moves inside and changes into a partial derivative. So that's the central part. However, there was also this part. So this part, let me go and zoom out. So in the 1D case, this part right here basically corresponds to the part in the center, but then there's also these two sides to it that drop all the way down. And the same thing happens here. So there's a central part, but then there's also this area underneath that's above these crescents, but underneath the surface that also goes ahead and affects the integral when it changes with respect to time. So, okay, so going back to the graph. So basically, however, there is one factor that can be neglected. So going back to the monitor again. So in the monitor, it turns out this area right here doesn't have to be taken into account. And the same thing basically happens with this graph. The area that's both between the two functions, between these two layers, and inside of the little slivers on either side of the primary zone, this area actually can be neglected. So instead of having to consider this when considering how the integral changes with time, it's only necessary to consider that surface. So the goal now is to basically find the area under each of these slices, which is basically the equivalent of finding the areas under here and here. Shrinking that. Okay. So basically there's going to be an area added, a little area delta A plus that's added, or rather a little volume that's going to be the volume above this sliver here, and that depends on the function above it, the functional top, integrated over the area. And then there's going to be another volume, there's going to be a volume removed, which is designated by delta A negative, which is also topped by the function at T naught. And this is what's going to be the change in the integral that's caused by the time dependence of A. So basically the next step is to look at what's going on underneath that. So go back to the whiteboard. So the 2D Leibniz Rule. So basically what's going on is there's going to be some kind of shape. And this shape is basically going to move with time. So it's going to come up and take some kind of new form. And the inside is basically the area of the shape is basically referred to as A of t. But then the boundary is going to be referred to as omega of t. So omega of t is defined as the boundary of A of t. And when it moves, it's going to move to a new location, and that's going to become omega at a new time, which is t plus tilde. So this is the boundary at a new time. So is actually needs to be done is to basically compute what the area is under the function but above these area locations. So above that and above this. So to see this sketched out, let's go to the sketch. So basically, this is the edge right here. This is the area here. So this is the area here, and then looking at it from the side. So basically there's some area on the base that's bounded by these omegas at t naught and t plus delta. And then there's a function above it, and the function has some sort of shape that might bend or curve. That's above this area. So what's going to be neglected is the difference in the function from here to here. The function at the top of this is going to be considered flat in the sense across the line, but it's not flat in the sense of the entire distance. As it goes along the curve, the function value is going to change. But as it goes across the curve, it's going to be considered, in the direction of velocity, it's going to be considered flat. So basically there's this function here, these two different boundaries, and the boundaries are essentially moving outward with a velocity, u vector, which is basically determined by the flow field. So in some areas, these boundaries could be moving faster than others. So the idea is to try to compute this area, these little areas, around points on the boundary, and then multiply them by the function at that point. So it's basically computing the area. So this is basically the function at that point is going to be multiplied by that little slice of area that is determined by the velocity field going outwards across this little sliver right there on the surface. So to do this, there's basically the velocity field, and then there's n hat is basically defined as the normal to the velocity field. So what ultimately happens is the idea is to figure out what the area is. So to figure out the area, there's this area that comes from the velocity field as it moves across. So that's, and then there's this derivative of s. So the idea is to find this area to multiply by that point, the blue point there. And so in order to do this, there's a fundamental theorem in geometry that says the area of a parallelogram basically equals the width times the height. So the area of this pink area equals the width, which is the ds, which is the interval along the curve, times the height, and the height is actually n hat dotted with u, which is the velocity vector, times the delta in t, the change in time. So then basically, so another way of looking at this, just doing this over again, is I basically draw this boundary, and this is omega with respect to t. And then I have it moving outwards. And I decide, and I look at some point here, which is going to be B, just called Bx, By. This is some point on the boundary. So basically what the definition of Bx and By is Bx, Y are going to be a member of the set of points on this boundary at T naught. It's actually T naught. And then this function, of course, moves. So now it's at T naught plus delta here. And there's this little interval which is going to be ds, which is basically a distance along the curve. So the question, so if this thing is basically moving, so I'm going to draw it again. No, maybe I won't. So here's a, so if there's some kind of u velocity that's going across here, the u vector. So what was just shown is basically that the delta, which is the distance across here, which I actually do need to draw this one more time because it's getting too crowded. So I'm going to draw this again, the same figure. Well, it's supposed to be the same figure. So this is omega t plus delta, and this is omega t naught. And I've got some point here. So there's basically a distance across here, which is basically that distance, and that'll be delta. So essentially delta is going to equal n hat, which is the normal vector, which I'm going to end up drawing attached to this because there's not enough room elsewhere. So here's the normal vector, which is actually supposed to be normal to that. So that's a normal vector. So it's a normal vector dot product with the u vector, and okay, and then it's times the little interval of time, because that's the time interval multiplies by the derivative in the velocity to get the distance. So basically the area swept out, so this little area that's going to be swept out around here, so there's an area in there, so the area swept out opposite to this point Bx, By is going to be the delta times the ds, so that equals n hat dot u vector delta ds. And then there's another trick that's important here. And so then the question is, what is the volume? Swept out. So this is, as I already said, so we'll go back to looking at the 1D case. So in the 1D case, there's a function f, and then here's x. And there's basically a b down like that, and then at a different point in time it might be doing something different. So this is f of t naught plus delta, and this is f of t naught. So basically, suppose there's also this boundary here. I'm actually going to do that in a different color. So here is the boundary. Well, it starts out, this is b of t naught. And then the boundary basically moves to another location. T naught plus delta. So what's important is there was a little point here. And now as it happens, it was, so this point is at f of b of t naught, comma t naught, is where that point is located. And then there's an area in here. So there's some area that's swept out. Now it turns out that this area can be calculated simply by using the point here, where the boundary was at t naught, and just cutting straight across. It doesn't have to take into account that it actually moved up, because that's a second order effect. So what happens is this, what's actually comes out in the equation is, of course, f of b t naught, comma t naught, derivative of the boundary t naught, and then times the delta would actually indicate what the area is that's swept out. And the same thing happens here. It's not necessary to use concern. So what happens in the 2D case is basically the same thing. It doesn't matter what the function is over here, it only matters what the function is at bx, by. So it suffices to use a function of bx, comma by, which is actually along the boundary at t naught, comma t naught, to compute volume. So ultimately, volume swept out is going to equal this guy times the function. So it's going to equal the function of bx, comma by, comma T naught times the area of the base, which is, I'm going to reverse auto hill U vector and hat ds. So this is the volume swept out of a little area. So that's basically the volume swept out of what is a small area. So it's swept out. The volume that's swept out is hill. So one of these little areas around the point, what is it? So just one of these little segments around hill. So to actually get the entire area that's in this swivel, it's under the graph, but between these two positions of the area, this has to be done for all of these little points. So this is basically going to be the sum for all of these blue points. This has to be done again and again and summed. And the sum in this case is actually effectively just an integral. So, go back to whiteboard. So ultimately, here, so for each, so for each, let's draw this thing again. This blue. And then draw these guys. Small. So we're going to slice this up into these guys. So for each of these guys, we have this equation of bx. And this is the bx, comma by. And this is at omega t. At time t. And then u vector dot product and hat ds. So that's what's up here. So another way of writing this is to write out explicitly what bx and by, well, let's see. So this is basically another way of writing this is writing this at, well, this would be basically b. Well, right now I'm going to keep it as a bx and by. So another way of writing this could be considered to be x, the x naught, I, and y naught, I. So that would be like the ith. So this could be like 0, and this would be 1 for the index. And this would be the ith index, and then it goes up, keeps going on. So if each of these things were labeled as a count, and then this would be summed up to go ahead and get the approximation. But the other way to do this is to just do this with the integral. So basically this is the integral of the function of x, comma y. Let's go ahead and evaluate it. T u vector dot n hat ds integrated over the boundary at a given time, we will x and y, of course, in this integral are members of the boundary. That's kind of by the definition of the integral. So this is basically a line integral where it basically integrates along all of these points, all of these bx's and by's, and sums them all up, multiplies by ds, so that basically gets the entire area. So at the end of the day, there's two parts to this integral. So this has basically explained what the change in the integral is due to the motion. So this was the original integral, which is this integral over a of t with the function of x, y, t by dt y, and then the part, so for part due motion of t, or another time dependence of at, that equals what's just been derived above, which is the boundary integral with the function y, t, and then the velocity of the boundary field, which determines the velocity of the boundary, times the n hat, which is the normal vector at each point on the boundary, and then the individual distance along the boundary, ds. And then the other part of the integral was basically the same thing, this thing, but this is due to the change in the function itself in because the function itself changes shape with time. And this part equals the integral over the area, as it was originally, the integral over the area, and then with a partial derivative moved inside. And this is a function of x, y, t, and dx, dy. So, to write this whole thing out, I think I'll go over to the graph first. Let's go to the graph. So looking at the graph, so basically this is what's going on. So the area in the middle, where the function basically changes with time, that's done by the partial, and then the two boundaries are basically done by the boundary integral that goes ahead and multiplies the values of the function on the boundary by this quantity that is dependent on the velocity of the field, which is basically the velocity of the boundary at that point. And one thing here is this doesn't have explicitly a minus sign. However, when u is in the opposite direction from n hat, so the n hat is always going to point outwards. So if u, in this case, u is moving equally in that direction, so this will actually automatically become a minus sign. So this still subtracts that volume there. And then the entire equation is basically put together which is the change in time of the entire integral over the area. And this has both parts in it. So to put it all together, basically going to put down the equation. So this is the entire equation. So this is d by dt integral over the area as a function of time the function of x, y, and t, and of course dx, dy, the area integral, and then this thing equals the first part, which is the integral over the area again, and then the partial derivative of the function with respect to t, x, y, t, this is dx, dy, and added up the integral over the boundary as a function of t, the function again, x comma y comma t, and then the velocity field, which is a function of x and y, and it's also a function of time itself, dot product with n hat, which is of course changes as it goes around the integral because it's always perpendicular to the boundary, and then ds. And sometimes this is actually just combined and written as ds vector. Means the same thing. So basically starts with the integral of the derivative of an integral over an area, and basically progresses to be a partial derivative of the integral over the area, and then a boundary derivative that involves the velocity. So that is the 2D version of Leibniz Rule, which will be important in deriving the Euler equation. In fact, that's most of the work actually involved in deriving the Euler equation right there. And I sure want to do one more thing. And I basically show these together. So this is the comparison. So this is the original 1D case, which is you can show that the derivative is in the middle, and then there's the function and along the function along what's the boundary in both cases, multiplied by the velocity, what's effectively the velocity outward to the boundary, which is what this is doing. And in this case, it's split into two parts. In this one, because the u dotted with the n turns negative, here it doesn't need to be explicitly written in two parts, because that's actually taken into account by the direction of the n hat. And then here's the equation in all its awful glory. And it will show up again shortly in the derivation of the Euler equation in the next video, where the Euler derivation will resume.